So next one is the image segmentation. So image segment is nothing but the image is divided into groups. After dividing into groups, if you process with the entire lung, for example, if you take a lung image, if you process the entire lung image, it will take a longer time to analyze. It will take to analyze the images, it will take more time. So in order to reduce the complexity, we have to segment that entire lung into a partition, into subgroups, and we have to label it. So each segment we have to label it. So this is called as image segmentation. So here the first method is the K-means algorithm. So first we have to segregate, we have to separate, make into three groups or any number of groups. So in my lung cancer, for detection of lung cancer, I can use three regions, three groups. One is your background region, and next one is the lung region, and next is the cancer region. So I'm splitting as three regions. Okay, so when we use this K-means algorithm, so how the segmentation will take place is, first it will compare one pixel with the neighboring pixel. If both the values are same, it will put into this background. So it will check the background region fully. It will compare all the pixels in the background region and put all the values here. And similarly, the lung region, it will compare all the pixels one by one and it will put it here. So this is the second group. Like that, we have to make it as a two to three groups. So K-means algorithm, it will compare all the values and it put it in only one group and another group and make this group as empty. So if this group is empty, so suppose if there is a lung node is present in this region, that information is missed. So this algorithm will give very less accuracy when we use K-means algorithm. So this K-means algorithm always gives empty clusters. So this will affect the accuracy. And when coming to the fuzzy C-means, in fuzzy C-means, instead of these three groups, when you run for the first time, I'm getting background, lung region, and cancer region. When I run for the second time, it will give the lung region, then background region, and the cancer region. When I run for the third time, it will give lung region, cancer region, and background. See, in the case of background region, you have lung region and this. So decision making is very difficult when you use this fuzzy C-means. So that will also affect to detect the cancer nodules accurately. So the next method is artificial bee colony. So these are the methods that I have implemented in my research. So artificial bee colony. So artificial bee colony is a very interesting story. How the bees searching for its food. That concept is implemented in this. So when you see the bees life, how it is collecting the food is, we have three types of bees. One is the So we have three types of bees. One is you have employee bee, onlooker bee, and scout bee. Three bees. So first, the onlooker bee will select some of the employee bees and give information to go and search for the food source. So food source is nothing but it may be a jasmine flower, or it may be a sunflower, or any flowers, okay, which is present in there. So the employee bee will go for a search for the food source, and it finds some places and give the information to the onlooker bee. So the onlooker bee choose some other employee bees, tell the places, these are the places you have the food source, go and collect the honey. So these bees will go there and get the go there and collect the honey. Once the honey is filled, it will come and inform to the onlooker bee. So some employee bees, they couldn't find the place, they couldn't find the flowers because already many employee bees have taken now. So they couldn't find the place. So those bees will be converted into scout bee, and they'll go to another places to search for its food. So this is the concept. This concept is implemented in this artificial bee colony. So here the three bees, right? Here I've taken the bees as one is the lung region, cancer region, and background. Three regions. Okay. So After finding this lung region, first lung region, you have to compare the pixels in the lung region and compare the values. If it is same as, it put it in one group. Once that all the pixel, so we have to fix to that some target. So some 500 or like that, we have to fix. We have to develop the program, write the program in such a way. Once this is full, then it will move to the next. So once all the pixels are completed, we will label as background region. Then go to the next. It will compare the values in the lung region. If that is full, then name it as a lung region. Like that, we have to segment it. So this is in this way, we have to segment using this artificial bee colony. So the drawback that I found in this artificial bee colony is it is doing only local search. So local search is nothing but, suppose if I have this is the cancer and you have this is the lung region. So this is the background region, this is the lung region. So maybe somewhere here have some nodules will be present. So it will compare the pixel value of only this pixel and this pixel, this and this, this and this, and lung region this and this. Okay. So since it's doing only the only particular area, only the particular region. Suppose if a lung nodule is present instead of here, if it is present in this case, so these informations will be missed if it is not properly segmented. So that is the drawback that I found in this artificial bee colony. To overcome that, I have developed a new algorithm, that is D-Lion ABC algorithm. D-Lion is nothing but deep lion algorithm. So this algorithm is based on the concept how the lion search for its food. So how the lion will search for food? So lion will not choose a small area. So it will choose a wider area. So some 10 lions will be will be located in different areas. If they find any animal, so all the lions will come in different directions and attack that animal. So that concept is applied here. That means what is that wider range is nothing but it is a global search. Instead of comparing the values in the background region itself, I have to compare this value with this one. Compare this value with this one. So by comparing the global pixels, global search, this will give better result when compared to this artificial bee colony. So these are some of the results that I got from these methods. The first, this is the input image, and this is the ground truth image. So ground truth image is nothing but, so one side, if I know this image, so where is that lung nodule will be presented? Where is the lung nodule in this image? That will be identified only by the radiologist. So the radiologist will mark the image of the lung nodule and they will give. So views from that only we can understand, we can validate our results, whether what we have found is correct or not. So this is the ground truth images. The radiologists have marked where is the actual lung nodule. So when compared to the other methods like K-means algorithm, FCM and artificial bee colony, see here it is predicted in other areas also when compared to the original image. But D-line algorithm has correctly segmented properly as in the case of the ground truth images. So next one is the feature extraction. So once the segmentation is done, the next one is extracting the features. So from the segmented images, we have to extract the information that we call it as features. So there are three types of features. One is the color features, then shape features and texture features. The color features is nothing but it will give the histogram is color. So we can use the histogram of gradient method to identify the color features. And shape features, we can use volumetric features and geometric features to identify the shape features. And texture, we'll use the wavelet transform also to find the texture and the local binary pattern. So these are some, I will tell you some of the algorithm that is used for this feature extraction. The first one is the intensity features or the color features. So histogram of gradient. Histogram of gradient is nothing but finding the color values at the edges. Gradient means edges. how to find finding the color value edges, that features will be taken for the color features. So for example, so color features we have 0 to 255. Color features are there. That means 256. Okay. So in this 256, I'm just splitting that into some array of colors. So suppose I'm dividing it as a 10 divided by 10. So what you'll get? I'll get 25. So that means you have 25 array of elements. The first will be 0 to 10 color, and the second is the 11 to 20, and 21 to 30. Like that, it goes on. The array will goes on. So it will compare the pixels values, and if it belongs to this color, means it will be located in this region. Okay, so if it is in this, means it here. So likewise, all the pixels will be compared, and based on the intensity value, it will be selected. So first, when you're comparing the pixel value, if the pixel value is very high when compared to the other things, then that we call it as an edge. So edge will have the high intensity value. So that edge, that high values will be segregated, and that will be taken as a features for this intensity features values. So in this way, we got the intensity features from histogram of gradient. And coming to the texture feature, texture is nothing but a repeated pattern. If we have a repeated pattern, then we call that as a, if we say the grass will not be one grass will not, all the grass will be of same pattern, right? So these things we call it as texture features. There are many methods are there, but this local binary pattern is a method where we can get good results in LBP. So here, so this PC represents your central pixel, and these are all P0, P1, P2, P3. These are all neighboring pixel. Okay. So here we have to make a condition that if the central pixel is greater than or equal to your neighboring pixel, for example, P0. If it is greater, means you have to put the value 1. If the central pixel is less than your neighboring pixel, P0, then the value is 0. So likewise, you will get the values 1, 0, 1, 0, 1, 1, 0, 1, like that. So this will give us one binary value. This binary value, we have to convert that into a decimal value. So that gives the features. So that is the feature obtained from the local binary pattern. And next comes the shape features. So we cannot say that lung cancer nodule will be of a particular shape. It may be any shape. So here I have listed out some of the shapes, irregular shapes. So for processing these irregular shapes, other methods we cannot use. We have to use this scale invariant Fourier transform to identify the features to get the features from these methods. So scale invariant Fourier transform is nothing but if there is a size changes, variation in the size, then we can go for this scale invariant transform. That means, so in the test image, I'm giving this shape. So let it be 50 cross 50. So in the training image, you will have like this type of image, this type, maybe 150 cross 150. Let it take an example. Size wise, okay. So here the size, so I see this size and this size gets varied. But if you see that this dimension also will get varied. The only thing which is not varied is the feature corners. So here the corner will be in this. Here also this is the corner, and this is the corner here. Here also this is the corner. So the corner points will be same in all the even though the size varies, the corners will not be varied. It will be the same. So you have to find the corner features. That means how to find the corner features, again comparing the pixel value. If they have the very high value of if you have the difference is very high, then we call that as an edge. If you're connecting two edge, that will give us a corner. From that, you have to identify the corner features. So that is this method. This method will find only the corner features. And next one is Zernike moment. Zernike moment is used for the angle of orientation. Suppose if my image Suppose if my image is of this shape, and this is the testing image, and in the training image, my image of like this. Both are same, but it is inverted. Its angle of rotation is changed, orientation is changed. So for such cases, you have to use this Zernike moment. So what this Zernike moment is, it will rotate it to 360 degree. It will rotate the image to 360 degree. So when it is 0 degree, the features will be extracted. When it is at 30 degree, the features will be extracted. 60, 90, like that. For all 360 degrees, all the features will be extracted. So when it is in this position, it will, suppose if it in this position means it will find what are all connected to that. So that features will be, those features will be extracted and it will be processed for the next case. So this is about the Zernike moment. So these are some of the results that I got for the intensity features, shape, and the color features. So these results we got. So all the when you see the features, all the values will be it is a numerical values. So we'll get the values like this. From using these features, we have to go for the classification. For the classification, we have to define classes. Okay, from the features, we have to define a class. For example, if it is a lung cancer, for identifying the lung cancer, I have to categorize. One is malignant, benign. So we have to, from the features, you have to define which category, whether it is a malignant or it is a benign. So these, all these will have a formula. You have to apply the formula and get the features. So next one is the classification. So classification is nothing but we have to classify the given image into some whatever we have defined initially. So if we take the lung cancer, two classes I said, one is benign and malignant. So when by analyzing the features, it will predict whether it is a benign feature or benign or it is a malignant tumor. So in classification, always it will compare with the training images. So in the classifier, when we use these three classifiers will not have more number of images. But when you go for the CNN classifier, we need thousands above images are needed to get the accurate result. Okay, so so how this classification will happen is when I give a test image, this is the test image, and here you have, for example, I'm having hundreds of training images. Okay, so this is TR1, TR1, 2, 3, like that it goes up to TR100, TR100. So when I give the test image, so this test image will compare with the 1, 2, 3, 4, 5, like that you compare all the 100 images and check what is the which test image is close to the training image. For example, TR2 is close means it will make this TR2. Then TR11 is so TR11. Like that it will. So you will have some number of images which predicted the tumors. So this TR1 maybe it may be malignant. This is also malignant. This may be given as benign. So whatever it may be, it will collect all the. It will classify all these things. Okay, and then using some confusion, we have a confusion matrix. Using the confusion matrix, we have to find the accuracy. Because in this case, it is predicted like malignant as well as benign. So how many are malignant? How many are benign? So from that, you have to find the accuracy. In that way, only this classifier role plays how much efficiently it can predict the disease. So first one is the SVM classifier. So SVM classifier, as I told before, from the extraction, feature extraction, you have collected some set of features. So these features will be given to the SVM classifier. For example, in SVM classifier, you have to find the border value. So border value is nothing but you have sets of features. For example, when I'm giving an image, from this image, I can collect some 20 or 50 features I got from this image. So in the set of 50 features, find what is the minimum feature and what is the maximum feature. So this will give the border value. So for the test image, this is the test image and here you have the training image. So for the test image, you know the border value, let it be 10, 50. That is the border value that I got for the test image. So this will compare with all the training images. So which is as the closeness to this training image. So suppose if it is even if it is 10.1, it will consider. It will take because it's very close to that value. So those values will be taken, and it will be considered. It will be classified whether it is but that image is a malignant or benign. It may be malignant or it may be benign. So this is the SVM classifier, and the next is the Navy base classifier. So Navy base classifier is nothing but it will find the weight function, weight value. So when I say weight value, if we have 50 features, add all the features values and divided by that 50, will get some value. That is the weight value of that particular image using. Okay. So then after finding this weight value, again compare with the training image. So which training image it is close to this testing image. So that will be predicted and that will be classified. So this is Navy. I'm giving only the overall view. We have a detailed algorithm. We don't have that much time to explain each and every algorithm in a detailed manner. I'm just giving the overview of all the classifiers. And the next one is the bagging classifier. Bagging classifier is nothing but it will form a bag. So how it form a bag? So from the set of features, first it will take all the similar features. So similar features means it may be 5, 5, 5, 10, 10, 10. So many features will be repeated one. 5, you can give 5, then 10. All the values can be given, and those will be put it in the similar features. And the next one is non-similar features, which is not at all similar. 10 and next 50 that will be put in the second bag, and third bag, which are all very close to the features. For all very close to the features. So 10.1, 10.01. So these are all very close to the okay. So first it form a bag. After forming the bag, when you give a test forming the first, it will form all the bags, all the regions. So when you give the test image also will form a bag, like a three bags. Okay. So this will compare with the training images. So for which image is closest? So always it compare the training image. The closeness will be predicted, and that will be classified. Okay. And the next one is the CNN classifier. It is the convolution neural network classifier. So convolution neural network classifier is a classifier which is it is very much used to extract the deep features, more features. So when we use these algorithm will extract the features and it will classify. But CNN will take deep features. If you're taking more number of features, we'll get the detection will be more accurate. Okay. So when compared to others, SVM and other methods, they will use from the image. They will take the other process will take place. First one is the noise will take place, then removal of noise, next segmentation. After segmentation, feature extraction. Okay, but in convolution neural network, we have to give only the image. So this image will automatically extract the features and finally it will give the result, whether it is what category that will be given. So here this is the input image. So this is the input image. Okay. So from the input image, next you have the convolution layer. So convolution layer is nothing but filter pre-processing only, filter technique. So from the image, it will take the corners, edges, and it will remove the noises. Okay. So more number of convolution layer, more noises will be removed. And the next is the pooling layer. So here you have a pooling layer is nothing but feature extraction. From the convolution layer, it will extract the features. Okay, it will extract the features. And here we have two methods. One is average pooling and max pooling. Average pooling, it will take all the pixel values. It will find the maximum average of that value. That value gives the feature. In max pooling, from the pixel value, find the maximum value. That maximum will give the maximum pooling. Like that for all the images. So for I'm using 100 images, 1000 images. For all the 1000 images, it will do both the convolution as well as the pooling layer. And the next, this is the input to this one. This convolution layer will give an input to the pooling layers. The pooling layer will extract the features, and again it gives to the this goes to the next level. So initially it has taken only the corners and edges, then it go in deep into the low level features, and it will extract, it will remove the noise in that, and that will be given to the next layer. Next is again a pooling layer, where more features will be extracted from this convolution layers. Okay, like that. If you have three to five means 5 convolution layer, 5 noise will be 5 times the noise will be removed, and features will be extracted. So here I have taken 3 convolution layers. So from this image I have extracted 1080 features that I got extracted from this CNN classifier. So, and finally, this will be connected to the fully connected layer. So like what we are doing in the artificial neural network, we are giving the features, then it find the weight value, and all these processes, the same will be carried out here. And finally, it will find the categories, whether it's malignant or benign. So this is the actual working of this CNN. So I've used, these are the algorithms I've used for this classifier. And when compared to other things, so this CNN gives the better results when compared to this. So before, when we do the features extraction, once we extract the features, next one is very important. One is feature selection. So feature selection is nothing but we have to remove the repeated features, and irrelevant features are removed by using the feature selection. So if I'm having some 150 features, and in that 150 features I have some many repeated features are there, irrelevant features are there. So if I process with that image, it takes some time to execute it. Okay, so the speed of that execution is very high when compared to CNN. So if you remove all those repeated features and irrelevant features, and we choose only the selected features, and if we process, then the recovery speed or the execution speed is very high. So these are all the image processing techniques. Image processing techniques. So the image processing plays a main role in this robotic surgery. So once if you get an image, all the process will be carried out, and once we find whether it is first stage of cancer or second stage of cancer or third stage of cancer, based on the stages of cancer, the robotic surgery, that means the robots will give the drugs to the patients accordingly based on the condition. So that what is the patient condition, that can be obtained only from the image processing technique. So image process plays a major role